Hello and welcome to Physics Frontiers episode number 66, The Limit of General Relativity with James Owen Weatherall. Jim is a philosopher of physics in the Department of Logic and Philosophy of Science at the University of California at Irvine. And today we will be discussing his paper, Where Does General Relativity Break Down? Show notes for this episode can be found at frontiers.physicsfm.com/66. Show notes include the paper we read for this podcast, other papers, related episodes of Physics Frontiers, and so on. And now, Jim Weatherall. Jim, how are you doing?
I'm good.
The thing I wanted to talk about was your paper, Where Does General Relativity Break Down? And I thought that was really interesting. I mean, where things break down is always interesting. That's the best thing, right? At least as far as a physicist is concerned. That's where we want to push towards, is where does it look like this theory will fail? And if you were an experimentalist, you say, okay, how can I make it fail? If you're a theoretician, you probably know better than me, but I expect you want to see, well, what different ways might it fail? And are those still really physical, right? Because you can make all sorts of math that breaks things down that's not physical. And I thought you had a pretty interesting take on that. And, I'd just like to talk to you about that. And I think I'd like to just start with your take on general relativity as an effective theory before we start talking about the different ways it might break down and what those mean.
Yeah, sure. Historically, there have really been two very different ways of thinking about general relativity. One way that emerged out of a tradition of people who are primarily interested in general relativity itself, possibly with cosmological applications, questions about the status of singularities, black holes, things like that. And who, beginning with Roger Penrose and his group back in the 60s, you start seeing a very mathematical, very geometrical way of thinking about general relativity. And this was really valuable. It clarified a whole bunch of things that earlier generations of physicists had really just gotten wrong about general relativity. Things like, where is there a singularity in Schwarzschild spacetime describing a non-rotating black hole? Is it at the event horizon, or is it at the center of the black hole, or there are singularities in both places? It turns out that people's answers to that question had a lot to do with confusion about how to use coordinates and coordinate changes and stuff like that. A sort of more mathematical, more geometrical approach has completely cleared that up and was really fruitful. So that tradition has continued. People still do that, sometimes in physics departments, sometimes in math departments, frankly, sometimes in philosophy departments. Of course, there's another tradition that started a bit later that also comes out of work in cosmology, but work in cosmology that's really coming out of particle physics. And in that tradition, the standard model of particle physics, right, you have these quantum Yang-Mills theories. They're geometrical in a way, but it's really hard to think of them as geometrical in a quantum context. And so people use other kinds of methods. In order to make sense of these and get any kinds of predictions out, you need to renormalize them. And of course, there was this revolution in thinking about renormalization group theory that happened in the early 1970s, right around the time the standard model sort of took on its modern form, right? Work by Ken Wilson and his collaborators. Now, all of the theories that we develop in particle physics are effective theories. They're theories that apply at particular energy scales. They're expected to break down at high energies. If you have a high energy theory, you can use the renormalization group to run down to lower energies, derive what the low energy theory would be given your high energy theory. And you can use similar kinds of arguments to predict where you would need a still higher energy theory to run down to your current high energy theory, right? And so you can sort of predict that at certain energy scales, things are becoming pathological in your current high energy theory, and that some other new still higher energy theory is going to supersede it. Okay, and so if you're thinking about particle physics in that way, you're thinking about quantum Yang-Mills theory and the standard model in that context. We think those are going to break down at high energies. We know that we have low energy theories that do break down at energies that we know about, and we need the standard model to supersede them, to fill in what happens when we get past that breakdown point. And you're now trying to fit particle physics in with general relativity, particularly in the context of early universe cosmology and later in the context of black holes. It's very natural to think, well, we've got one classical field theory, we've got a bunch of quantum field theories. It's going to be the case we're going to want general relativity to be quantized in some way, be on par with these other quantum theories. There are real conceptual problems if that doesn't happen. And practical, just theoretical problems. And once we quantize it, we are going to expect it to be just like any other quantum field theory, in the sense that these sort of renormalization group type arguments are going to apply. And in fact, we can even think of classical general relativity as itself being a low energy effective field theory. Probably not in the exact same sense, right? The kind of mathematical methods that we use for renormalization kind of depend on the details of quantum field theory as we understand it. But from a broad perspective, where we have different theories that break down at different energy scales that are going to be effective in some regimes and not effective at other regimes. From that perspective, we can think of, Newtonian gravitation as a very low energy theory. General relativity is a somewhat higher energy theory. Some future quantum theory of gravity, maybe some intermediate kind of, effective theory of gravity. And then maybe there's going to be some grand unified theory or string theory or something like that in the very high energy regime from which all of these, the standard model theories and some form of quantum or semi-classical gravity will be low energy versions of that. From that point of view, just like we expect our standard model theories to break down at some scale, we should expect classical general relativity to break down at some scale. And we should maybe even expect an intermediate quantum theory of gravity to break down at a grand unified scale, or like a string theory scale, a Planck scale, something like that.
I mean, we talked about this on the show a little while ago with deformed special relativity, which is trying to take some ideas from quantum gravity and pull it down to special relativity without going either through general relativity or through quantum field theory first. Pretty sure that it failed. Mm-hmm. Whatever they were doing doesn't seem to have worked correctly. Uh-huh. But that's what you mean by an effect field theory. In this case, you're looking at things where there's a superior, I shouldn't say superior, but a superior theory that becomes something simpler, let's say. Maybe not simpler, but probably simpler when you reduce the energy in it. Right?
Yeah, I mean, think about, as just a classic example, quantum electrodynamics, the Feynman, Dirac, and Schwinger theory of photon-electron interactions, right? The first successful quantum field theory. We now think of that not as it's not a fundamental theory by any means. In fact, it's a low energy version of electroweak theory. We know that, in fact, there's a further symmetry that electromagnetism and the weak force are unified at certain scales, that you have photons and W and Z bosons are all force carriers of this one single force. Or in fact, maybe a better way of thinking about it is photons and some of these other lower energy things are sort of superpositions of, or combinations, I should say, of the real force carriers in electroweak theory. And we can show how, as you run to lower energies, this kind of unification breaks down. These two theories come apart. You get a weak theory and you get electromagnetism or quantum electrodynamics. The picture would be something like you'd have some high energy theory that was playing the role of electroweak theory, and then you'd have some sort of low energy theory that's playing the role of QED.
Okay, and here you want to do something similar with general relativity. And you're saying, well, there are these physical effects, and want to see what sort of environment these physical effects are actually in, and what do they have in common, and things like that. Could you describe how you're thinking of that? I
should just be clear. That particular part is not in any way my idea, right? So this is the way that people have been thinking about general relativity for a very long time, that we ought to think of it as an effective theory, kind of like the way QED is an effective theory, kind of like the way that probably the standard model is an effective field theory for some high energy unified theory. The question, though, is how do we think about general relativity within this framework of effective field theories? In particular, there are a couple of different lines of thought on what it would mean for general relativity to break down and how general relativity will break down. So one thing that you very, very often hear is that, look, general relativity has these singularities. Singularities reflect some kind of breakdown in the theory, but they probably aren't physical. We shouldn't expect that, in fact, we could be going about our business and then, the Earth will fall into some hole in space-time. But the theory seems to allow that kind of possibility. In fact, space-time can just end. It can just, it can be sort of littered with places where things can't continue. That just seems weird. It seems like something's going wrong there, and that part of the theory needs to be superseded by something. So that line of thought is something you hear very, very often, that, singularities, generally speaking, are unphysical and reflect a breakdown of the theory. There's another thing you hear often, and this is in the context of this language of effective theories that I've just been describing, which is that low energy theories or effective theories break down at some characteristic energy scale. You'll hear things like the standard model has to break down at the Planck scale because that's where quantum gravity has to be unified with these other forces. Or you'll talk about the electroweak symmetry breaking scale and the breakdown of QED and things like that. And so the idea is, and this is just part of the formalism of effective field theories in particle physics, renormalization group methods, is that there's some energy scale that characterizes the breakdown of the theory. The problem is, and this is one of the sort of big issues that I try to take up in the paper, is that there's a mismatch between these two ways of thinking. Because in general relativity, it's not really clear what we mean by high energy. It turns out that it's been extremely difficult to define a notion of gravitational energy in general relativity that meets all of the things that we would want it to meet, all the criteria we would want it to meet. That it would be locally defined, that it would be non-vanishing in cases where you have high-frequency gravitational waves, for instance, things that you would think of as really energetic phenomena in the theory. And so it's kind of hard to know how to think about energy in general relativity in the first place. Moreover, there are singularities in space-time. You can come up with examples of solutions to Einstein's equation in general relativity that have singularities, but where there's no curvature, where everything seems really, really well behaved and kind of benign, kind of non-energetic by any intuitive measure, even though there's a singularity there. And so it looks like we don't even really know what high energy means in this context, but whatever it means, we've got these cases in general relativity where the theory appears to be breaking down and people want to say some successor theory is going to fix our problems, but where it doesn't seem as if energy is playing any role. We can't say, well, it's because it's a high energy regime that we need a new theory. So the first thing I try to do is make sense of how to solve that tension. In what sense can we expect some future successor theory that modifies general relativity in the high energy regime, whatever we're going to mean by that? In what sense is that going to be expected to generically resolve singularities?
And you went through several of those. I think you said there was a sort of strong field regime was where you could really look at things breaking down.
Yeah, so what I end up arguing is that energy is kind of a red herring. We shouldn't worry about coming up with the notion of energy here. That what we should do is think about where general relativity sort of implies the most dramatic effects on matter. So often the right way of thinking about this is in terms of tidal forces. Right. So where is it in general relativity that you're going to have bodies that are sort of getting pulled apart by gravitational effects? And this is sort of intuitive from the point of view of our ordinary ways of thinking about gravity, right? Tidal effects on the Earth, like literal tides, are due to the gravitational influence of the moon. And when that influence is strongest, you have sort of the oceans getting pulled apart. And when it's sort of weaker, they're sort of not pulled apart as much. And so you get this oblong shape, and that's what the tides are. So that's a differential in gravitational influence that's reflected by tidal forces. And that's measured. I mean, that's perfectly clear how that works in general relativity. That's measured by curvature. Now, there are issues of thinking about curvature as an energy, and there are issues with thinking about curvature as a scale, because curvature is a tensor. It's coordinate dependent. It's observer dependent. You can have disagreements about what curvature is. And so what I suggest, and I think that this is keeping with things that people have said in the literature previously, but to solve other kinds of problems, is that what we really need to do is look at curvature scalars, which are quantities that are constructed from curvature, which, roughly speaking, measure the size of curvature relative to itself, or relative to the metric, or relative to sort of natural standards that are around that don't involve introducing coordinates or a particular observer frame of reference. And thinking of those curvature scalars as our best measure of, as you say, the strong field regime or the relativistic analog of a high energy regime. Even though I think we really shouldn't think of that as measuring energy, although it's probably the best we can do, it's not perfect.
Okay, so you had several reasons for that. So I guess after this, the question I have is, does general relativity fail at high energy? That's, I guess, the next section. And you talk there about geodesic incompleteness and Cauchy horizons. Yeah,
so you get two questions here, right? So one, what do we mean by high energy? And as I say, I don't think that there's a perfect answer to that. Curvature scalars are the best measure we've got of the strong field regime, which is what we ought to be thinking about. But there are a whole bunch of different curvature scalars lying around, and some of them can vanish when other ones become very large. And so it's not totally clear why we should look at one and not others. I think, in fact, we have to look at a bunch of different curvature scalars. But now here's another problem. Suppose that we agree that divergent curvature scalars signal a high energy regime, or just very, very large curvature scalars signal a high energy regime or a strong field regime. Is that the only time that general relativity breaks down? right? Because if the idea is that we're going to come up with a new theory that supersedes general relativity just in the very strong field regime or the high energy regime, but general relativity breaks down in regimes where curvature vanishes or where curvature is very small, then it's really not clear why we should think this new theory is going to solve some of these problems, some of these things that we thought were unphysical in the theory as we have it now. And so I point to a bunch of places where curvature is small or vanishing, including curvature scalars, and yet there's some sense in which the theory is divergent or the theory breaks down or becomes singular or has some other kind of pathology. So just as an example, you can come up with spacetimes where curvature scalars all vanish, even though the curvature tensor, in a certain sense, becomes divergent, where the theory is clearly breaking down in a way that looks like it ought to count as a high energy breakdown. These are gravitational wave solutions that are analogous to electromagnetic waves that are in a certain sense null. And so electromagnetic energy density actually vanishes, even though the waves can have some divergent behavior. Now, these have to be kind of finely tuned. Are they all that physical? I don't want to argue that they are. I think that they're kind of interesting cases to keep in mind. They show that it's possible for some kind of divergent behavior to happen without curvature scalars seeing it. But there are other kinds of examples too. The way that people usually talk about singularities in general relativity is in terms of geodesic incompleteness, is the idea that you could have a trajectory that an observer or a particle could be following that stops after finite time and can't continue. And once again, you can have geodesically incomplete spacetimes that are flat. So there's, again, some kind of singular behavior that isn't captured by these curvature scalars. But I want to just grant that these are kind of unphysical. I mean, you can come up with solutions to Einstein's equation that have this character. They aren't solutions that you would get sort of starting with ordinary matter fields, giving some initial conditions, and then seeing what happens dynamically by solving the equations. You have to sort of construct them almost by hand. And so you might think, look, the physically relevant regimes of general relativity are the ones that we get from real matter influencing geometry via Einstein's equation in a kind of dynamical way, like via an initial value formulation. Let's just agree that that's what we really mean. In that case, I don't have a theorem, but it's pretty plausible that the kinds of singularities you're going to get are going to be the kinds of singularities that arise due to really, really high matter densities leading to really, really large curvature. And that generally speaking, you should expect those singularities to be singularities that are associated with divergent curvature scalars. So this all looks good. Like black holes are like this, right? Gravitational collapse is going to lead to curvature singularities, singularities where curvature scalars diverge. Big Bang is like this, going backwards in time. Matter density was very, very large. Curvature was very large. You're going to have a curvature singularity. Future big crunch scenario, similar kind of thing. Okay. So that partly answers the question, does general relativity only break down in the case where curvature scalars diverge? And the answer is not exactly, but for practical purposes, I think we should say yes, as long as we're only talking about singularities. But there's another totally different sense in which general relativity can break down, which is Cauchy horizons. So I mentioned the initial value formulation of general relativity. The idea here is that Einstein's equation can be thought of as a system of equations that have it's not exactly a well-posed initial value problem in the traditional sense, but it's close enough. You give me initial data, there exists an essentially unique solution. And in fact, there exists an essentially unique maximal solution for that initial data. But sometimes that essentially unique maximal solution actually isn't maximal in the sense that it's the biggest solution to Einstein's equation you can find. It's maximal in the sense that the initial value formulation breaks down, and you have to use other methods to come up with a larger solution. And so the picture you should have in mind is a situation where you've specified how the entire universe is at a time. And then you've just let the laws of physics tell you how things should evolve, right? How the matter should evolve, how the geometry should evolve. All of this is coupled via Einstein's equation. You've got a universe evolving over time, and then that whole picture breaks down. And the theory doesn't tell you what happens next, at least using those kinds of methods or that kind of picture. Instead, what you have to do is come up with a kind of global solution, usually involving closed time-like curves, so a kind of time travel that allows you to extend the universe past where this initial value formulation is broken down. And that sure looks to me like a sense in which the theory is breaking down, or at least some qualitative change is happening. And now you might be tempted to say, there's something really unphysical there. The problem is that happens in rotating black holes. And so we just got a picture of Sagittarius A star. I mean, maybe naive, but a straightforward reading of general relativity says, look, that thing is rotating, probably rotating. And inside its event horizon, if it's a rotating black hole, there's going to be a point where this Cauchy horizon occurs, where this initial value formulation breaks down, and beyond the horizon, you're going to have closed time-like curves. And so how do we rule that out? I mean, this seems like the natural general relativistic description of these kinds of real astrophysical objects, things that we can see colliding with one another now that we can take pictures of, seems to predict the existence of a Cauchy horizon, not in the observable regime, but beyond the event horizon. So is that a sense in which general relativity breaks down in a Kerr black hole? So in something like Sagittarius A star, that Cauchy horizon does not occur in a high energy regime. In a normal Kerr spacetime, and the rotating black hole solution to general relativity that people use to model these things, the Cauchy horizon is in a relatively low curvature regime. And so this argument that I've given that we should expect general relativity to break down in the presence of large curvature scalars doesn't apply there. And so now it's not clear, should we expect quantum gravity to solve the Cauchy horizon problem? Or do we think closed time-like curves are real? How should we interpret this kind of situation?
Yeah, I mean, at first glance, you wouldn't look at quantum gravity for something that's that large, right?
Yeah.
You expect quantum gravity to be tiny little pieces of space-time down at the very bottom of the scale, well below what we can see now. And closed time-like curves give people the creeps, really. So you're going to relate this to the strong cosmic censorship hypothesis. I don't know if you have enough time to talk about that, but I thought that was really interesting when you went through that, especially since as a conjecture, it's not precise. And I thought that was really interesting to hear about that. So do you think you can talk a little about that?
Yeah, absolutely. Yeah. So the strong cosmic censorship hypothesis is this idea that goes back to Penrose in the 60s and early 70s. Just at the beginning of this period where people were starting to think about these large-scale issues in general relativity from a geometrical perspective. And the observation that these spinning black holes had this kind of breakdown of an initial value formulation is very old. People have known about this since at least the 60s. And so people agreed back then that this was kind of unphysical. And there was this idea that although we had clear examples where you had an initial value formulation, you had a solution that resulted, you had a Cauchy horizon, you had an extension, right? We had this rotating black hole example where all of those things were satisfied. The idea was that somehow this was anomalous, that generically this wouldn't happen, that if you just gave me some arbitrarily chosen initial data and tried to evolve it, that you might get a Cauchy horizon, you might get to a point where you can't evolve any further, but that there wouldn't be some further extension past that you wouldn't have an extendable maximal global evolution, that you wouldn't have this kind of breakdown of determinism and closed time-like curves. Now, Penrose had this kind of intuitive idea. Over the following 60 years, people have come up with a bunch of different, more precise statements. And in fact, the idea, there was the cosmic censorship hypothesis, there was the strong cosmic censorship hypothesis, there's the weak cosmic censorship hypothesis, a whole bunch of different variants on these things that people have tried to prove or to disprove or to study in particular cases. People have tried to get at this idea of generic initial data by thinking about stability. So the idea being that anytime that you had something like the Kerr solution where you had an extendable Cauchy horizon, that if you sort of fiddled with the initial data, even just made small changes, that situation would break down, that somehow you might still get a Cauchy horizon, but you wouldn't be able to extend further. And a lot of really exciting work on this. This is maybe the most active area in mathematical general relativity over the last 10 or 15 years, even longer. A lot of really, really interesting work has been done on this, and some very striking claims have been made about it. But because the original conjectures were pretty intuitively stated, the precise mathematical claim that people have been trying to prove has been a bit of a moving target. And the exciting new work has been on versions of the claim that people have been able to make progress on, which is not necessarily the version of the claim that's most relevant for other purposes. And so what I have in mind here is this paper that got a ton of attention when it first appeared on the archive by Jonathan Luke and Mihalis de Fermos, where they show that in the specific case of a rotating black hole, if you perturb the initial data that leads to the standard Kerr solution just a little bit, you do get a Cauchy horizon, but you can extend past the Cauchy horizon. And that looks like it's a counterexample. to the strong cosmic censorship hypothesis, that small perturbations don't prevent the extendability and don't prevent closed time-like curves. And so maybe it's not going to be the case that generic initial data is not going to have this kind of pathological feature. And so really interesting work. I mean, they even say in the paper, this shows that the particular version of the strong cosmic censorship hypothesis that they're thinking about is false. And that's all right. I'm not questioning that. But what I want to point out is that if you're interested in the question of whether or not quantum gravity is relevant to what happens at Cauchy horizons, and if you're thinking about how to answer that question in terms of whether or not Cauchy horizons are generically associated with a high energy regime, and you agree with me that we should think about that in terms of curvature or curvature scalars, the version of the strong cosmic censorship hypothesis that they have disproved is not the version that you should care about. Because the version you should care about is going to ask whether or not you can extend curvature across the Cauchy horizon. In particular, what they do is they ask, well, is there a metric that continuously extends past the Cauchy horizon? But curvature is like the second derivative of the metric. And continuous extension doesn't imply that the derivatives of the metric can be extended, right? I mean, there's going to be some point where those are not defined or they're divergent or, something goes wrong, right? You imagine like a continuous function with a divergent first derivative. If the physically relevant thing was the first derivative, you could still have a breakdown even though it looks like the whole thing is continuous. And so what I argue is that this paper that's been widely interpreted as showing a version of the strong cosmic censorship hypothesis is false actually should be interpreted as providing a really important piece of evidence that the physically relevant strong cosmic censorship hypothesis, the one that we should care about from the point of view of whether or not Cauchy horizons will be resolved by a high energy successor to general relativity, is true. So their paper actually gives an argument. It's a conjecture, it's not a full proof, but they sort of give some plausibility arguments that, in fact, you should expect not to have that curvature can extend continuously through this horizon. The curvature should blow up. You get what they call weak null singularities at the Cauchy horizon. And so what this suggests is that, in fact, the strong cosmic censorship hypothesis, that would matter for the question of whether or not Cauchy horizons will signal a breakdown of general relativity that will be, fixed by a quantum theory of gravity, might in fact be true. It doesn't prove it as a single example. You want to show that, in fact, for all generic initial data, curvature blows up at the Cauchy horizon. And then you would want to interpret that as saying, well, and that means that we're in the high energy regime, and therefore quantum gravity will be relevant, and we won't get closed time-like curves. And so, yeah, a lot of what I've talked about before is kind of stage setting for that argument that the version of the strong cosmic censorship we should care about is this version that has to do with curvature, and that their counterexample actually isn't a counterexample to that version. If anything, it makes it more likely that it's true.
I guess what you're saying is the continuous formulation of the strong cosmic censorship hypothesis isn't the one you're looking for, right? You're saying that if you're looking at this C2 description, this second derivative description for the curvature, it's the one you're looking for. And what I have written down here is that strong cosmic censorship hypothesis means that Cauchy horizons are a high energy phenomena if we're talking about that curvature as that high energy thing that you're saying. And what I have here is a punchline. This is exactly what you said. If quantum gravity resolves the curvature singularities, then it should also solve the Cauchy horizon problem.
That's right. That's my perspective. And I think it's looking increasingly plausible that that's, I don't know about the quantum gravity side, but if quantum gravity is going to step in and change things in the regimes where curvature scalars are large, I think it's looking increasingly plausible that Cauchy horizons generically will fall in that regime. Again, it's generically, we know of examples where that won't happen in the same way that we know of examples where gravitational waves and things diverge, but curvature scalars don't see it. In the same way that we know that there can be singularities in flat spacetime. But these all rely on, really strong symmetry assumptions and things that we may have good reason to think couldn't actually be realized in nature, and that the kinds of situations that could have evolved dynamically given the known laws of physics and the kinds of matter we have and everything are going to fall into this other category where Cauchy horizons 2 will count as high energy. Cauchy horizons 2 will get resolved by quantum gravity.
All right. Excellent. I think that's everything that I had. Did you have anything else that you wanted to say?
No, that's yeah.
Okay, well, perfect. I think this was great, and thank you very much.
Thanks, Jim.
Okay, thanks. This has been Physics Frontiers episode number 66, The Limit of General Relativity with James Owen Weatherall. Show notes for this episode can be found at frontiers.physicsfm.com. Show notes include links to the paper we read for this podcast, Where Does General Relativity Break Down by James Owen Weatherall, as well as links to other papers we may have mentioned and related episodes of Physics Frontiers. Also in there's a little extra from my discussion with James about how philosophers of physics work with physicists on problems such as this one or other foundational issues. So I'd like to thank Jim once again for coming on, and I'd like to thank you for listening. Bye now.